Jonathan is going to have Amish to tell us about the results from the first magnetic survey of pulsating gamma door stars. Over to you, Jonathan.
Great. Yeah, thanks for the intro. So I'm John Labadie-Bartz, currently a postdoc at TTU Space, but almost all this work was done in France at the Paris Observatory. So as I think we know by now, there's a lot of different classes of pulsators and a lot of stars observed with magnetic fields at the surface. And there's a growing interest in combining these two subfields to use pulsating stars to learn about the physical strength and geometry of magnetic fields inside of stars and see how that affects their structure and evolution. So the specific type of star that we were probing with this project are intermediate mass G-mode pulsators. What's nice about these stars is they have kind of characteristic frequency spacing patterns that allows us to probe deep into the core regions. And what's especially nice is that their later evolutionary products, red giants, are also amenable to astroseismology. And we see some disconnects between the main sequence gamma door stars and the red giants, indicating that there are some inadequacies in our theoretical understanding of the interiors. So we want to see if internal magnetism is relevant in how these stars evolve. So in principle, this is an easy task. We try to find stars that have rotational modulation due to spots on the surface caused by magnetic fields, and gamma door pulsation, just a bunch of G-modes. We observe those with Espadon, get nice Stokes speed profiles, and measure the magnetic field. So to do this, we selected 50 gamma door stars that seemed like they had rotational modulation, observed them with Espadon, trying to detect fossil fields with 100 Gauss or stronger. The short version is we didn't find any. So we had a bunch of magnetic non-detections. So these are small plots, but you're not really supposed to see any features. There's just basically nothing in the Stokes speed profiles. Now we did have a few magnetic detections, but all of these 4 cases where we found strong magnetic fields were kind of oddballs. They weren't exactly what we were looking for, such as this case that ended up being a spectroscopic binary that has a strong magnetic field in one of the 2 stars. It also has high-frequency P-mode pulsations that belong to the magnetic component, and lower-frequency gamma door pulsations that seem to belong to the non-magnetic star. So cases like this are interesting. For example, as far as I know, this is the first intermediate mass magnetic star in a close binary with P-modes. It's worth following up and studying further. But again, it's not the sort of gamma door systems we were looking for. So in conclusion, we really did not find any direct evidence of strong fossil fields in gamma door stars. All our magnetic detections were not kind of the typical gamma door star we're looking for. And that might suggest some connection between the subsurface convection zones that power gamma door pulsation and fossil fields. But I should mention that weak and small-scale dynamo-driven fields can definitely still exist in these stars. We were only probing large-scale strong fields. And, of course, internal magnetic fields are still allowed. So one takeaway is that magneto-astroseismic models for this class of stars can pretty safely set a global surface field of 100 Gauss or less. And that's that.
Thank you very much. Any questions, including online?
Victor, hello, Mr. de Moncton. Thank you very much for a very interesting presentation. I would like to ask what the signal-to-noise ratio was for your spectra and how many spectra you have obtained for your target.
Yeah, for most of them, we aimed for just one snapshot observation to test for the presence of magnetism. The specific signal-to-noise depended a lot on the both V sin I of the star. So we had a combination of very broad line stars and very narrow line stars, and the spectral type, which gives us different LSD gains. I can't quote the exact signal-to-noise number because they were all different. They were all calculated specifically to achieve a detection threshold of 100 Gauss. So can't specifically answer that question. But
okay, thank you very much. And let's thank our speaker again.